Welcome to another unit in this preparatory course, Mathematics. This time I'm going to talk about logarithms, what logarithms are, and which rules apply to working with logarithms. Well, first off, logarithm, that's basically if you have function as here, a to the power of x equal to b, and you're still looking for x. As compared to the part with the roots, where the x was actually in the base, here the x is in the exponent. And whenever you want to get to the exponent, that's where you have to work with logarithms. So here, if I want to actually solve this equation for the x, that's where I'm going to use a logarithm. So if I want to have the solution to the equation 3 to the power of x equal to 9, that's where I have to apply a logarithm. Ideally, I apply the logarithm specifically designed for this particular base. So here I have a base of 3, so I could apply the logarithm to the base 3. So as said here, apply logarithm to both sides. So here I can either apply the logarithm to a base of 3, then directly get the solution, or I can use any logarithm, which is here implied by the logarithm as is, the log as is. And then I have a rule where I can pull the exponent from the expression a to the power of x in front of the logarithm. We're going to see this in 1 or 2 slides as well. So if I pull this in front, I can then simply divide by log a and get my solution for x. Well, log b, so what was on the right side, divided by log a, so the logarithm of the base, this is what we also call then the logarithm to the base a of the value b. However, well, not every calculator can calculate a logarithm for any base, but almost all halfway decent calculators can at least calculate one type of logarithm. Well, you don't need more than one type because you simply calculate the logarithm for any base for b divided by the corresponding logarithm for a. Then you get any logarithm for any base you want. And well, also, if I look back to the first line here, what I need to keep in mind are two particular things. First off, the base always needs to be positive, and the value I apply the logarithm to, so the right side of this equation, also needs to be positive. And if I say positive, I mean strictly positive. So it's also not allowed to be 0, because I need to be able to calculate the logarithm of a and of b. And the logarithm can only be calculated for strictly positive values. So if I then, well, with those comments, switch back to my example with the 3 to the power of x equal to 9. So here I can simply calculate logarithm of 9 divided by logarithm of 3, or as I said, the logarithm to the base 3 of 9. In either case, I will get as a solution 2. Well, that's how basically working with logarithm goes. However, as I said, logarithms are only defined for positive real numbers. So the basis has to be positive. And I can also recall, as I stressed in the part on working with exponents, any number to the power of 0 is always 1. So switching this around, the logarithm to any base of 1 is always 0. So that's what I can draw from my, well, insights from the session on working with exponents and powers. Also, as I mentioned, the logarithm for any base of 0 is not defined, so we can only calculate logarithms for strictly positive real numbers. Then we have different types of logarithms. If we have a logarithm to the base of 10, sometimes you also write this as LG. If I have a logarithm to the base of 2, in some cases you write this as logarithm dualis or LD. And that's the most common one, the logarithm to the base E. E, that's the so-called Euler number, roughly 2.8. And here we write this as ln, the natural logarithm. And that's usually the one you find in almost all calculators. So usually we go with working with the ln. So with this as notation, we can then also stress that the ln of E, or in general, the logarithm to base A of A is always 1. So if I then take a look at the rule I mentioned before, so E to the power of A is A. So in other words, the logarithm and the corresponding base function cancel each other out. That's again more or less something which I could also have deducted from what I talked about in the slides before. But we can recall here, logarithm and corresponding exponential function cancel each other out. In particular, here the exponential function x of A, or e to the power of A, and the natural logarithm cancel each other out. And then we have 3 rules. We basically mentioned one of them already. First one is the logarithm of b times c can be dragged apart into the logarithm of b plus the logarithm of c. And this only works in this way, so if you have the logarithm of b plus c, you cannot separate this. So only if in the logarithm we have times and outside the logarithm we have plus. So here logarithm to base of 3 of 9 times 27 can be written as the logarithm to the base of 3 of 9 plus the logarithm to base of 3 of 27. So we get 2 plus 3, which is 5. Well, if we can do this with multiplication, we can also do this with division. So the logarithm of b divided by c is simply logarithm of b minus logarithm of c. Well, this rule is basically not so much a rule by itself, but can be deduced from the rule before and the rule after this. Why? We will see in a moment. Here, however, you could also recall if it's divided by c, it's minus. So for example, if I here have logarithm to base of 2 of 8 divided by 4, I can write this as logarithm to base of 2 of 8 minus logarithm to base of 2 of 4, which gives me 3 minus 1, which then is 1. Because also it's the logarithm of for base of 2 of 2. And here I mentioned whenever I take a logarithm of the corresponding base, I will always get 1. We had this rule on the slide before. And finally, that's the rule I also applied before. If I have any logarithm, so here log a to b to the power of d, I can always pull the exponent in front of the logarithm. In particular, if I have like an exponent of minus 1, I could also pull this in front. And that's why the second rule also makes sense. b divided by c is nothing else than b times c to the power of minus 1. So I first apply the first rule, and then I apply the second rule and pull the minus 1 in front of the log of c to the power of minus 1. So first and third rule give second rule. And well, here again an example. If I have log to the power of 2 of 8 to the power of 10, can simply pull the 10 in front. Then I have log to the base of 2 of 8. So I get 10 times 3. And well, again, where can we use this? We can use this in particular again to make some functions easier to be derived. And also, from an economics point of view, that's basically where the first rule comes into play. If we have formulas with absolute terms, where the absolute terms are multiplied, and you want to switch to growth rates, that's where you basically use the first rule, because growth rates can also be calculated based on the logarithmic formula. And well, that's then already all I wanted to say in the context of logarithms. So see you next time, and goodbye.